All right, guys, welcome back to our ongoing discussion about the quantum mechanics of absorption of light by matter. And we ended the last section with this example of a one-dimensional box and this idea of quantized energy levels. So now let's consider what happens when a light wave or a photon interacts with matter that can absorb that light. And specifically, let's think about it from a quantum mechanical point of view. What does it mean when matter absorbs light? Well, to think about that in the context as we've been going over this, let's postulate that our matter, our molecule, for example, can exist in one of two states, right? State it will give wave function sub 1, right? Where the system normally is found. And then an excited state, we'll call this the ground state, all right? And then distribution of the system or state of the system, we'll give psi sub 2. We're going to call this the excited state. Now, this is the state that has absorbed the light, for example, right? Okay. And so another way to think about this is that absorption of the light is going to perturb state 1 into state 2. All right. Now, further, let's suppose that both state 1 and state 2, or the state of the molecule described by wave function 1 and wave function 2, are both eigenstates of the time-independent Schrodinger equation, like we talked about the last time. Now, if that's true, the following also has to be true. We can write that down. Remember that time-independent Schrodinger equation involves this time-independent Hamiltonian, right, applied to the ground state. If the ground state of our system is an eigenfunction of this time-invariant, time-independent Hamiltonian, that would mean the following application of that Hamiltonian would have to just give us the energy back times the wave function, right? Okay, and let's assume that state 2, the excited state, also fulfills the same criteria, right? So we'd have then the energy following application of that Hamiltonian to the excited state. Okay, now from the discussion we had the last time, we know that this condition, that these wave functions are eigenfunctions of that time-invariant, time-independent Hamiltonian. We can describe, based on the little derivation I went through the last time, the time dependence of this wave function, these wave functions. They would have to look something like this, right? Which is that the time dependence of the ground state, right? Here's a function of time, has to simply be equal to a 0 time, or the value of that wave function at 0 time, or in the or the value of that wave function only as a function of the positions of the constituents of the system, times e to the minus I e divided by, E1t divided by h bar, right? And likewise, for our excited state, time dependence of that system would have to be simply equal to the time independent, the 0 time magnitude of the wave function times e to the minus I energy of that state, t divided by h bar. Okay, great, so that's cool. So we now basically have simple expressions for the time dependence of our ground state and the excited state, with this simple assumption that both states satisfy the time independent Schrodinger equation, and that they are eigenstates of, or eigenfunctions of that time invariant Hamiltonian. Okay, but remember, we're talking about the light being absorbed by this material, right? So we know that that Hamiltonian that we need to worry about here, we've got another component. Before, we were sort of ignoring the potential energy component in the particle in a one-dimensional box, right? Because remember, right, those Hamiltonian, right, is the sum of that kinetic energy and that potential energy Hamiltonian, right? And in this case, the kinetic energy, right, one we've basically taken into account. We showed you how to do that before, and we sort of ignored the potential energy one. But remember, what we've got going on here is light is this oscillating time-dependent electric field that's varying, right? So we have a time component in the Hamiltonian, in the Hamiltonian we're going to need here, okay? When we think about the application of light, all right, which means we have to write this in a somewhat different way, right? Okay, so what we really need now is a Hamiltonian that takes that into account, and that would look something like this. We can sort of write out a Hamiltonian, right? That's going to be, we'll call it a prime, right? That is equal to this sort of time invariant Hamiltonian component, all right, that has time invariant or time independent kinetic and potential energy components, right? They're not varying times, so we don't worry about it. And all the time dependent parts of this Hamiltonian H prime are contained in now a potential energy operator that is a function of time. Okay, and all of that is going to come from this time-dependent behavior of this oscillating electromagnetic wave that is the light impinging on this molecule that we want to understand how it absorbs the light, right? Okay. All right, so now what we got to do is sort of construct somehow a wave function that we can work with, right? And then figure out what we need in this from this Hamiltonian, along with an overall wave function that we could then substitute into the Schrodinger equation and try and solve it, right? Okay. All right. Well, it turns out that our system's fairly simple. We're only allowing two states, this ground state and this excited state. We can combine the wave functions for each of those two states and be a linear combination, turns out. And any linear combination of wave functions is also a wave function. So the wave function we would need for this system, including both of these states, would just look something like this. This C1, I'll explain what that coefficient is here in a minute, times the ground state amplitude, that's, you know, that time invariant e to the minus I, energy of that state, T divided by h bar, plus C2 time the time invariant amplitude of the excited state, right, times e to the minus I, energy of that state, time divided by h bar. So essentially, if you look here, what I've done is simply take the wave functions we defined for the excited state and the ground state, right, here, and we've just sort of combined them into a single wave function, right? These two coefficients here, C2, C1, those are related to the probability, or those specify the probability that at a given point in time, because they're functions of time, the system is either in state 1 or state 2, right? So they're sort of probability multipliers. They're integrated, or their sum is going to equal 1 at any given time, but they're going to specify whether the system's more probably in state 1 or state 2. Okay, now our goal here, what we really want to understand, right, fundamentally, is the rate at which light drives the system from state 1 to state 2. Right? That's the fundamental thing we want to try and understand. So to do that, what we need to do is take that wave function, right? Substitute it back into the time-dependent Schrodinger equation, right? For our overall wave function, including both states, right? And solve this baby, right? Okay. But we can't quite do that yet, right? There's something we're missing, right? And the thing we're missing is this. What does that look like, right? If we can't specify the time-dependent component of that overall Hamiltonian, we can't substitute anything in here, right? We can't do that, right? So we've got to think about a little bit more about what's the time dependent component of this potential energy operator. All right, turns out it's got a couple of parts, right? And one way to think about that, with analogy to the description I went through with that particle in a one-dimensional box. Remember, what we're thinking about here is, again, by analogy, this isn't a particle in a one-dimensional box, but if you think back to that, it illustrates something. Remember, when we solved that problem, we saw that the energy states of that system were quantized, if you recall that, right? So you can think about our system now as being sort of analogous to that, right? Where this, say, was maybe state 1 and this is state 2. And what we want to know, like I said, was how the light drives that transition from state 1 to state 2. And remember, it's been saying now we've got this time-dependent electromagnetic wave that's coming in here that's going to couple with the electronic structure of this molecule in some way and drive that transition, right? And that's sort of the really important part of what's going on here in this time-dependent potential energy operator, is the interaction of the electromagnetic field, right, of that incoming light wave with the electronic structure of the ground state of this molecule, how those guys interact with each other. Okay, and there are two components to this. The first, for electrically neutral molecules, the most important part of this for electrically neutral molecules, in terms of this potential time-dependent potential energy operator we need to specify, right? For electrically neutral molecules, the most important part of this is something known as the electric dipole operator. Right? And it looks something like this, where it gets a symbol like we saw before for dipoles, mu. It's an operator, so it gets a hat. And normally you would sort of bold that symbol to recognize that it's a vector, right? Because remember, we're thinking about dipoles, right? So we've got something that has a charge, magnitude, and an orientation. I can't do that very easily the way I'm doing this, so I'm going to use a different notation. I'm going to put a little arrow over it to recognize that this is a vector, right? Okay, and that is simply equal to the sum of over all charges or all particles that constitute the system of their magnitude, their charge magnitude, right? That E sub I times their position, right? Which is, I should also point out, their position. That's also going to be a vector, right? Because we're in space, so we got to think about orientation, right? So you calculate that electric dipole operator for a given state based upon applying that operator to the the charges and positions of all the particles in that state, right? Okay. Now we also now need to make another approximation because you've got lots of elements to these particles, right? You're thinking about the atoms in a molecule. You got nuclei, right? They're charged, and you've got the electrons, which is really what we're worrying about. And the reason we can think about this as just sort of so-called electronic or electric spectroscopy, or the spectroscopy of the electronic components of an atom, is because of an assumption that can be made in quantum mechanics for thinking about these kinds of transitions. That's a really good approximation. Essentially, that approximation is that we can ignore the nuclei, that for all intents and purposes, the nuclei and atoms that are going through these electronic transitions as a result of light being absorbed and pushing these transitions up and down, that the nuclei essentially don't move. They're essentially fixed in space, right? This is the so-called Frank-Condon principle. And it simplifies things quite a bit. It lets us essentially ignore having to do the calculations and think about what's going on with the nuclei and just focus on what's happening to the electrons and their probability distributions. They're essentially the structure of the electron clouds, where all this business is going to be happening. The nuclei are basically just fixed in space. Okay, right. So that's a pretty good approximation. These transitions happen really fast relative to the nuclear movements. So it's a really good approximation. It works really well. All right. So now we got to do something. Remember, again, we're trying to figure out what's the form of this potential energy operator that depends upon time. We've got part of it here in this electric dipole operator. Now we got to fold in what's messing with, or what's driving the application of this dipole operator. And that's, of course, the electric field, right? The electric field of the light here, right? Okay, well, that's actually relatively straightforward to specify. We saw that when I introduced the beginning of this to you guys from Maxwell's derivation of this cosine of this time varying electric field. I'm going to change the form of it, which is, it's fairly typical to do it this way. But using Euler's formula to switch from cosine to an exponential function, we have the amplitude at time 0. And again, remember, this is spatially oriented, right? So this is also a vector. So the maximum amplitude is 0, e to the minus I omega t, where t is time, I again is that imaginary thingy, imaginary number, right? Fundamental imaginary number. And that omega is now, this is the circular frequency of the light, right? Okay. So now it turns out all we need to specify that potential energy operator as a function of time is just to combine these two, and it's a simple multiplier, right? So the operator we need, time-dependent potential energy operator we need for the absorption of light, is simply equal to the product of that electric dipole operator, right, times the electric field operator, right, which would, written out, would look like this. Right? So that's all we would need. Taking that definition, applying it now to our Hamiltonian, so that again, we have the time invariant kinetic energy and potential energy subsumed in this h of q, and we add now what we've defined as this time-dependent potential energy operator that depends upon the dipole operator and the time variable electric field operator. We can now take this, define our Hamiltonian, go back to the Schrodinger equation, time-dependent Schrodinger equation, right? Whoops. kind of sloppy nomenclature here, isn't it? Right, right. As we did up here, right? And I'll just rewrite it here, right? Right, right. So now we've basically got what we need, right? We know what our time-dependent Hamiltonian looks like. We've got an expression for our wave function. Now all we need to do is substitute those guys in, go through some math, which is not trivial, and we can come out the backside with a description with what we're looking for, which is how fast, what's the rate at which a given potential energy operator, which would be governed by the light coming in, the particular characteristics, strength of the electric field of that light coming in, its frequency, and the properties of these two states. How fast does that system move from state one to state two? Okay, well, like I said, to do this, you have to plug this all in and go through a little math. Rather than get sidetracked on this, I'm just going to cut to the chase and give you the answer. Turns out that the rate of absorption of the light is proportional to this expression, the absolute value squared of the application of that dipole operator, that electric dipole operator, to the ground state multiplied by the complex conjugate of the excited state. And the absolute value, again, that's that Dirac notation. So application of the operator to the ground state multiplied by the complex conjugate at the excited state, integrated over space and time, normalized, absolute value of that squared, turns out to be proportional to the rate of absorption, right? So another way to think about this, and the reason I'm doing this is because the quantity inside that absolute value bracket it gets a name, right, that you should know about. Another way to think about this is that this value, or this expression, I should say, here, right, this is equivalent to a transition probability, if you want to think about it that way. Right? It tells you something about how readily the system transitions from state one to state two, and under the influence of this incident potential energy from this incoming light. Another way to think about it is it's sort of the ability, or it's proportional to the ability of the light to distort state one into state two. It's another way to think about it, right? So because we're talking about pushing electrons around, we're talking about rearranging electronic structure, and it's pretty clear from the fact that we're using something that is essentially a dipole operator here. The light is inducing a dipole. Remember, we started with an electrically neutral molecule. The light's absorbed. The electronic structure of the molecule rearranges under the influence of that electric field to induce a dipole. Okay, so this expression in the middle of this absolute value bracket, right? That expression, I'll just rewrite it over here. Gets a name, right? Specifically, this is known as the transition state dipole. Right? And importantly, because you remember what the components of this were, right? Remember, to solve this, right, we're talking about the induction of this dipole under an externally time-varying electric field. So because the absorbed light electric field varies with time, right? And because, therefore, our potential energy operator varies with time, right? That means, or these two ideas together, therefore require that the transition state dipole varies with time, right? So the probability of a transition from the ground state to the excited state varies with the time-dependent oscillations of the incoming electric field. So sometimes people will refer to these transition state dipoles as transition state oscillators, right? Because the probability of that transition changes as a function of time, as the incoming light field varies, right? Okay. All right. So that sort of gives you, hopefully, the sort of a grounding in some terminology you may have heard before that you'll come across, and what it sort of means, at least at a basic level of familiarity. But this is kind of abstract, right? So in the next section, I'm trying to make this a little bit more practical with some examples.